Alrighty, so this is the last big lecture of the OS course, and it contains the last two lectures that I've given face to face. Alright, so lectures 10 and 11, they're about input output and a little taste of files and cybersecurity. I mean, it's called computer security, but I mean, the buzzword that exists today in the job market is cybersecurity. And by the way, 80% of the job offers in Europe, they're oriented towards cybersecurity. So it's something that is really interesting, and there's a huge demand for that, both internship-wise, research-wise, research and development, and even in the normal job market. Um, what I'm gonna introduce in today's video is just a taste, as I said earlier. And if you're more curious, if you have more, if you're curious enough about this topic, you can use your favorite search engine to get to know a little bit more about it and explore a little bit more. So let's start with I/O, and then we're gonna tackle a subtopic of I/O, also known as disk, and to see how it's used as a secondary storage, as we've seen it both in the CA and in the OS, and notably in the CA when we talked about the memory hierarchy. And then a couple of words on files, the things that you need to know of in the context of this course, and then we're gonna tackle the security. All right, so this is an important aspect that you need to see. Where's my pointer? So what I did in my face-to-face lecture here is to make people try to figure out what's this schematic is all about, and try to figure something that is systematic. I mean, use your experience to identify the different components that are present here, and identify something that is systematic when it comes to, in a way or another, IOs. So here we can see our CPU. It's called the processor, and um, by now we're kind of having some kind of expertise when it comes to the CPU and the memory hierarchy, etc. And we can notice that there's a direct link between the processor and the cache, and this is true when we've seen the hierarchy of the storage, the memory hierarchy, that the cache is the closest thing to the processor because the registers are inside it. So basically the cache is the first level right after the registers. And then you can notice that there's some kind of bridge that deals with the memory. So there's some kind of an indirect link with the memory. However, the cache, we have direct link. So basically, when the processor needs something from the memory, the first thing that it will look in, without any intermediate component, is the cache. So this proves what we've seen earlier this year together. I mean, this semester together. And then we can see that we have some kind of peripheral component interconnect buses, PCI bus, right? And we have a bunch of other components that are connected through this bus, through an interface or some expansion, etc. And you can notice here a couple of things, that we have a bunch of disks. We have a bunch of disks here. We have a monitor here, and we have, we could have a keyboard. We could have some serial parallel board, all connected together through this particular bus. What your colleagues in the face-to-face lectures notice, that systematically when I have a component, it feels like I have some kind of controller that goes hand in hand with it. So basically, each peripheral that we have here, we need some kind of chip, some kind of controller, right? Hardware chip that would play the role of the interface, or will allow us to efficiently communicate and deal with a particular hardware component. And this is what we're gonna see in the I/O section of today's video. So yeah, here I've posted some pictures. I've projected some pictures during the face-to-face lecture, and I asked one of the students to identify the different hardware components that we're seeing here that we use in our everyday life. And we wanted to, I mean, the purpose of that is to identify different I/O categories. So I/Os are things that are going outside of the computer per se through the interfaces that we talked about. And as we said over and over again in both the OS and the CA courses, that the major components of a computer are systematically a CPU, a processor, right? We need there's no computer if we have no CPU unit in it. We need the memory definitely, because we're talking about the stored program paradigm. So basically we got the both instructions and data from the memory. And then one other major component, classical major component in a computer, are definitely the IO modules, right? They could go together or be separate, but I mean, from a logical point of view, there's one IO model from a logical point of view. All right, so here are the categories. So here we can see, for instance, a keyboard, a mouse, we can see a printer, and a monitor, a computer screen, or a bunch of screens federated together. Here for, I mean, you're kind of young, so you wouldn't know what that is, but this is a terminal, for instance. And the idea here is to identify those things are meant, you know, they're definitely I/O components, right? So they are peripherals connected through the computer, through the I/O controllers or modules. But the idea here is who is meant to deal with those peripherals. So who would be on the opposite side, on the end side of those peripherals? So from one side we have the computer, and the computer is connected, and they are connected to the computer on sitting in front of those and using them in order to be able to deal with the computers. You guessed it right, it is human users. So these are the IOs that are suitable for interacting with the computer, with a human computer user. Fair enough? And this is why we're going to go ahead and call them the category, their category, we're going to call it human readable. So they're, you know, meant to interact with the human being. So this is the first category, and then we're going to go ahead and jump to the second category, and we're going to get inspired from the first category to try to find the second category. So here we can see a disk, for instance, a bunch of sensors, actuators, whatever. And by the way, this is a computer from a car, and we're going to talk about that way more in the embedded system course next semester. And here you can see a USB stick, flash drive, whatever you call it, whatever you want to call it. So are those, I mean, can we put a human user here and use those to be able to interact with the computer? No. Basically, this is what we use to maybe store some data here, maybe put some MP3 or some videos on it, or some files, or the project, whatever. However, in order to be able to access them, we need to go through the human readable category to be able to use those. But those, they interface directly with the machine, so it feels like it's a machine to machine category here, right? So this category is suitable for interacting with the electronic components here, equipment or components, fair enough? And this is not human readable, it's on the opposite side of the human readable, which is machine readable. Fair enough? So we have category number 1 now, human, category number 2, machine, and let's try and figure out the last and final category. So to give you a hint, you're more maybe familiar with that. You've seen it at home, or you're at, I don't know where, but you've seen it somewhere here. Here, it's less likely that you've seen it, but this is what we used to use in order to be able to have some kind of data sent over phone lines and stuff like that. Alright, so you've guessed that this is a router, a Wi-Fi router, or a router, it doesn't really matter, a gateway, especially those who are taking networks or a network course. You should be familiar with that. So what does this category of I/O allow us to do? So instead of having a standalone computer, now the computer could be part of a bigger network, and then a bigger network, and then the biggest network, which is the internet at the end of the day. Right? So these are suitable for communication with remote devices. So, and we're going to call this category communication: human readable, machine readable, and communication IOs. Now, the step during class was to try and, you cannot, assume that all IOs are the same. First off, because we've seen that we have 3 different categories, and within the categories we can have some differences, because if you're dealing with the keyboard and dealing with the graphic display, well, it's not the same thing, because a keyboard is meant to be used, for instance, to input some characters from the human user, whether the display is meant to output a bunch of pixels, right, to be able to communicate or convey or let the computer spit out some information towards the human user. And it's not the same it's not the same device that we're using, and hence we need to have some kind of key differences between them. And in order to put you on the right track, and this is typically what I do in my exams, and you should be aware of that by now, I'm giving you this particular figure here, and we have some kind of numbers, and we can notice that from that one we can go ahead and draw some conclusions about the first key difference. For instance, if we're dealing with a keyboard and we're dealing with a graphic display, right, we can notice that the data rate, I'm going to call it this year the speed of data transfer, and we're going to see next year in the meta system course what is the official name of it and the common name of it, right? So the speed of data, you can notice that it's here, it's 0.01 kibibyte per second, whether here it's almost 30,000 kibibyte per second. So yeah, there's a huge difference between the two. First off, because the human inputs, whenever you're typing a character, well, you're not as fast as the machine. However, here you need to deal with a bunch of pixels, and depends on the resolutions, and you need to serve it real quick to make sure that there's a seamless display happening on the computer monitor. So yeah, first off, the speed of data transfer or the data rate, right? So there's a differences of magnitude, a huge difference between a keyboard, right, which is basically very slow compared to the graphic display. So this is one key difference. Go ahead, pause the video and try to imagine the difference, the other differences between the I/O devices. So what do you think? For instance, the characters that we input from a keyboard, they should be, coded in a way. Is it the same way to code the pixels in a graphic display? And go ahead and try and think about other differences, for instance. Alright, so now I'm assuming that you paused the video and you've written a couple of ideas, and then you're going to compare them to the actual ones that I'm going to give to you. So the application, we can find out that some I/O devices are meant to be used with different type of applications. However, one type of device could be dedicated, one application could be dedicated to one type of device. Like, you cannot use it with the different applications. So is there any, the different software support for each of the devices? How complex the control of the device is. So basically, we've talked earlier that each peripheral, so I/O component, systematically has some kind of controller, hardware controller that is integrated to it. So basically, if you're gonna crack open your computer monitor, you're gonna notice that there's a chip, electronic chip in your monitor that is interfacing the monitor itself, the display, with the I/O component inside of the computer, and hence there's some kind of translation happening there. And this is not only a hardware device, because it needs some kind of software support, very low level software support. And the face-to-face colleagues of yours, they guessed it correctly. Well, these type of things, whenever you're going to plug in a computer, plug in a new device to your computer, back in my days, not in yours anymore, well, before being able to use a new hardware component in your computer, you should definitely install something that we call the driver to it. And we used to do it manually, and nowadays it's now plug and play. So you still kind of need to install the driver and to be able to identify the device. However, it's the kernel and the operating system is way more developed nowadays than back in the days. So basically, you don't have to install it manually, but sometimes when you encounter some problems, you need to do it yourself manually. So yeah, it's good to know it from an engineering point of view. So yeah, so how complex is the device driver uh, of my particular I/O peripheral. So the general rule of thumb here, you can see that if you want to deal with a disk or even a keyboard or even a display, whatever, a network, right? It's not the same thing comparing to dealing with a printer, for instance. Maybe dealing with a keyboard is way easier because all you have to do is detect that the human user is pushing a particular key, and then you're going to go ahead and decrypt it, decipher it, whatever. Use the table, the proper table, depends on the coding scheme that you're using in order to get it. However, for a printer, it's not the same because you're going to go ahead and go from left to right, top to bottom, and you need to deal with the different pixels and make sure that you're using the exact colors in order to create the needed color at the very end, etc., etc. And the general rule of thumb here is, if I ask you today, and you should be able to answer this question here, what is the entity that is responsible of orchestrating everything inside a computer? You should know it by now, and it's definitely the kernel. So the drivers are here to to help out the kernel in managing the I/O devices. So the more developed the driver is, the easier for the kernel to deal with the I/O. So let me put it that way. If some engineers are hired to do the job and create a full driver that is capable of, managing every single aspect of the I/O device, the task of the kernel would be way easier because it's delegating the complexity to the actual driver. And it's the other way around. If the driver is not sophisticated enough, this means that the kernel itself needs to deal with the device. So complexity should be here. If it's not in the driver, it will systematically be at the kernel level, and this depends on the kernel that you're using, the drivers that you're using, etc., etc. All right. So this is red on white here. The effect of the operating system is definitely filtered by the complexity of the I/O module that controls the device. So the controller and hence the driver that is supporting it. If it's complex enough, it should be easier for the kernel to deal with it. Alright, more key differences. So the unit of transfer, are we talking about a stream of bytes or bigger blocks, etc.? So each device makes more sense. For instance, for disks, does it make any sense to have stream of bytes? Maybe not, because you need to deal with larger blocks to go ahead and be able to swap them in and out, etc. However, for a monitor, for instance, well, you're gonna go ahead and feed in real time the stream of bytes, so you can, if you're watching a movie or doing something on your monitor, or just navigating, well, you need to be able to update everything, so you're receiving a stream of bytes. The representation of the data. So how are you going to encode, right? So different devices have different coding, and take again, the keyboard versus the monitor, for instance. The keyboard, where we have some kind of encoding scheme. It could be Unicode, it could be anything. And then you have the pixel, how to deal with the RGB pixels, for instance, on a monitor. And finally, well, if there's some errors stemming, well, an error stemming from a keyboard, well, could be nothing compared to an error stemming from a disk, for instance, right? So the nature of the error, how to deal with them, how to report them, and what would be the consequences of having errors, for instance. So an error on the keyboard, maybe it could be just to make the user enter again a character. Whether an error on a disk or a storage device, for instance, could be the loss of data. So you can see that there's a difference between the two. Right? So knowing what we know now, can we propose a uniform and consistent approach to each and every I/O device out there? So we can we go like standard for everything? Well, naturally no, because you can see that you need to talk in different ways with each, and because we have different attributes for each, and differences for each of the I/O devices. So we need some kind of dictionary for each and every I/O device. So we cannot have a uniform and consistent approach to I/O. Now we're gonna go ahead and check the techniques for performing I/O. So one of the things, so I'm going to propose one of the things, one of the techniques, then you're going to pause the video and think of the other two. So programmed IO is one of the techniques. So basically, if I need to deal with an IO device, so I need to go ahead and get something from outside, well, a process could just be the responsible of going ahead and keep on listening in a way or another. So every now and then it's going to go ahead and check at the I/O module to see whether the information it needs is there or not. Fair enough? So let's imagine that you're expecting an input from the user, so from the keyboard. So the process will go ahead and check every now and then with a defined period of time whether the user has indeed entered or pressed a key or not yet. Fair enough? So this is what we call a busy wait. So all you have to do is, go ahead and each and every now and then you're gonna go and check and come back. The big question here is knowing what you know about the different states of the process that we talked about earlier in this course. So this means that my process, when it's busy waiting and it's being dealing with programmed I/O, so it's the process that is going ahead and checking whether the information is there or not. In which state exactly am I? So if I'm inside the processor and executing and doing the job myself, this means that I'm not in the ready state for sure because I'm busy, and I'm not blocked because I'm the one who's going and checking if the operation is there. I mean, the information is there, the operation is completed or not. So this is where I'm in the running state. It is up to me to go ahead and verify each now and then that's the information that I need is there or not. Is this something effective? Is it very efficient? Especially knowing me by now and knowing how much I care about performance. So well, you feel like nope, because first off, you'll be taking the place of another process that might do some actual job, and maybe there's another way to make sure that whenever the information is ready, go ahead and call me and let me know that it's there, so I can get it and continue my execution instead of wasting the CPU time just checking for the information if it's there or not. And this is what we covered earlier in the first lectures on this course, and it's interrupt driven. All right, so here we go, and so the process will gonna have some kind of system call to make sure that it needs some kind of information from the I/O, and hence when the information is ready, well, someone will let me know. And in this case, if I'm doing that, this means that I can give up my place to another. I could give up my place to some other process. Fair enough. So I can go, for instance, if the device that I'm expecting the information or the data from is busy, this means that I'm going to get blocked in a way, right? So I'm going to move from the running state to the block state. And whenever that information is there, well, the kernel, in a way or another, will inform me that your information is there, so you can go ahead and go back to the running state. Nope, not to the running state. You need to go through the ready state in order to be elected, as we talked earlier. So be extremely careful about that. All right, so this is a case where my process that needs the information, that asked for the information and expecting an interrupt, is getting blocked. Let us imagine, I imagined in the face-to-face lecture with all of your colleagues, well, how to have another possibility where my process that needs the I/O, right, will not move from the running state to the block state. So I don't want my process to be blocked. So the blocking, we've covered it, but I want to see how can I manage without making my process get blocked. So take a few seconds to think about it and then continue the video. So indeed, remember when we talked about multi-threading, for instance, so my process could be divided into multiple threads. So hence one of the threads could be dealing with the I/O, and the other threads within my process, well, they have nothing to do with the I/O. So the thread that is dealing with the I/O could indeed stop working, waiting for the signal, hence for the interrupt, to know that it could continue. And in parallel, I mean, at the same time, well, we can go ahead and pick any other thread from within the process to continue execution. Hence, the process will continue executing. So it's a non-blocking interrupt-driven I/O. Right, and the last thing that I tried to imagine with the face-to-face people is how to, you know, make my process do its thing and delegate everything to some other unit. And the other unit that we delegate to is called the direct memory access. So at the end of the day, if a process needs some kind of information from I/O, or wants to, you know, spit out or get some I/O, you know, some input, well, at the end of the day, it's going to place it somewhere, and that somewhere definitely, in order to use it, the data, well, it will be the memory. Fair enough? So engineers back in the days came up with a very effective solution, which is, well, let my process use some other, you know, delegate this task to some other component where it will ask the component to go ahead whenever the information is ready to get it and store it in the memory address where it's supposed to be, instead of the process itself taking care of that. Fair enough? So this is where a DMA module becomes handy. So it controls the exchange of data directly between the main memory and the I/O module without, you know, using the process, you know, without involving the process directly. So all the process does now is to ask the DMA module to go ahead and get the needed information and store it in the right place, or the other way around, like get the needed information stored in the right place from memory and spit it out to some output device. So let's dive a little bit into more detail of that particular technique here. We're seeing the CPU, and naturally, if I'm having a process inside the CPU, so this process is in which state exactly? So it should be in the running state. So this what would happen. The process inside the CPU send the request to the DMA, and it has some control logic, of course, the brains of the DMA. And it will request the direction of the data. So basically, do I need to read something from outside or write something to outside? Right? So it's either an input or an output. Once I've sent the request, I need to specify a couple of things. So first off is the number of words. I'm going to circle back to that in a moment. Most importantly, the I/O address. So basically, because a computer could be connected to many I/O devices, so I need to specify which one. And most importantly, where exactly in my memory I need to get the data from or to, if it's an input or an output. Fair enough? So these two are so obvious. So choice of the device and choice of the memory location to write or read from. But the big question is, why do I need the number of words, by the way? Well, simply, if you're going to go ahead and get something from outside, you need to make sure before you start the whole, you know, operation, if you have enough space in your main memory. Remember, because main memory is kind of restricted space-wise. So if the numbers of words are way larger than what you can afford, so basically the operation will not happen. Fair enough? Plus, the number of words could be used as a offset to the base if you're specifying the base address, so I will know how many things I'll be storing inside of my memory. Fair enough? And then, from a interrupt just information point of view, saying that everything was okay, you're good. So I've taken control of the DMA would say to the process that, all right, you asked me to do something, now it's done. So be aware of that. Right, so this is the blah blah of what I said earlier, so you can read it with rest eyes, doesn't really matter. And then no interrupt signal to CPU. That is exactly what I said. All right, so this is something that you need to read yourself thoroughly. These are the logical structures. So basically, remember, whenever I'm dealing with IOs and the user needs to deal with IOs, so there are different layers in a computer. So we have to go from the user point of view throughout the different layers all the way to the hardware that is completely transparent to the user, and then move. The services will be provided and moved all the way up to the user. So take your time reading it at home. It's completely thorough here, and you can understand it. Fair enough. And this is the most important part that I need to discuss with you. So here are the layers, and systematically by now, using what you've learned in this video, so this is the kernel IO structure. You can notice that there's a hardware and software part. So the blue is software, the gray is hardware. You can notice systematically that we have the different peripherals. And funny, you still see a floppy disk here. So the thing is, systematically each device has controller, as I said earlier. So this is still a hardware controller, and for each controller, well, we have some kind of driver. So this is the lowest layer driver software, which is called the driver. Now my question was, the question that I asked in class, to which category does this software belong to? Belong? And the answer is it's definitely system software, right? So this is something that is dealing with the hardware, so it's system software, and it's not meant to be dealt directly with the normal using non-administrator user. Fair enough. So here we feel like we have some kind of umbrella that will deal with different devices in order to make things smoother. The closer we get to the user, the more standard the different functions are, and then we have some kind of fork-like different branches here to deal particularly with each device, because as we've seen earlier, there are key differences between the different devices here. Fair enough. And this is how to interpret this particular schematic. One of the I/O devices are the disks. So at the end of the day, the disks, which are the secondary storage units or the secondary memory, are nothing but an I/O device that we connect through the bus, and that they have controllers, and we connect them to the bus in order to be able to maybe swap in and swap out some pages or some blocks of memory. It doesn't really matter how you call it now, in order to make things go smoother and faster in a computer. And this is where we can store the data, volatile or non-volatile, by the way. Do things disappear, flush away when we turn off a computer, a disk device? Nope, they're non-volatile, right? So let me show it to you. This is if you were ever curious enough to check a a hard drive, an external hard disk, for instance, or a disk, a hard disk inside of your computer. That's the same thing. You're gonna see that's made out of a bunch of disks, hence the name, by the way. And then you have different surfaces here. So those small disks are called platters, and then you have some kind of rod here. Technically, it's called a spindle. Doesn't really matter. And another rod here, and then you have a bunch of heads with arms, and then all you have to do is make the thing spin, and then move the head, the read-write head, in order to get the data that you need from. Now the question is how to, from a purely mechanical, geometrical, physical point of view, how to be able to store a lot of data and make it easy for us to read and faster. So this is how you divide a platter. So we have different tracks. These are the circles. And then each of the tracks is divided into sectors. So for instance, here we're seeing 2 tracks. And on each of the tracks that we're seeing, we're looking at n sectors. And this is where the data will be, the blocks of data will be. I want you to notice something else on that particular schematic here. You can notice something in blue and something in gray here. So here you feel like there's some kind of gap. So inner sector gap here, and then you can inner track gap. So the big question is, why is that? And it took us some time during class to try to discuss it and debate it, but it was an interesting debate. So one of your colleagues, I mean more than one of your colleagues, said that because these are mechanical devices, so basically when I want to read a block of data from here, right, well, I need to move the head and make the disk rotate and move the head to the exact beginning, right? So this makes sure that we have some kind of separation between the different first tracks and the different sectors within a track. But my question was, why make it thick? Why not very thin, just like delimited by the address, so basically barely nothing? Because we know the border, so this is the border. Why make it thick and make nothing here? So it's void here. You cannot do anything, and it's really void. So the answer is these are mechanical devices. So in time, if you use them over and over and over again, so basically maybe, well, they will be shifted a little bit. So instead of stopping right here, they will stop right there. And if they stop right there and attempt to read some data, well, they're trying to read data from the gap, and there's no data on the gap, so this will raise an error. Get it? From earlier. Remember the different errors that we could have with I/O devices. So yeah, it makes sense. It's a safety mechanism here. So if we do away with the safety mechanism, if we didn't have gaps per se, well, we would have not noticed that we're actually on a different sector and reading a different block of data, compared to the one that we requested. So if this one was very thin, well, the head will move by mistake to that particular sector, and then it will read the data from here, and hence it will consider that it's reading the correct data from the sector that I needed. So this is a safety mechanism. Alright, so what would happen when I want to read data? So first off, I need to wait for the device itself, so peripheral itself. And then we've seen that there's some kind of controller and I/O module that deals with the device, so I'm having to wait for that. And then we're waiting for the out I/O module. And then we're gonna go ahead and seek the particular track. So we're gonna move the arm for the particular track, and then rotate the disk in order to get to the sector that we need. And then only then we can start the transfer. So you can see that the data transfer is really short compared to all the waiting that I'm doing, in addition to the movement that I need in order to get to the right block of data to be able to transfer it. And this proves something that I told you way earlier when I talked about the memory hierarchy. Remember the triangle? So the farther we go, the more space we have to store data. However, it gets slower, and this is one of the things that will contribute, that will make things slower when it comes to secondary memory. It takes a lot of time to retrieve the data. Fair enough. So let's check some mathematical formulas here to understand a little bit how it works. So we said that speeds of disk compared to main memory are, it's very slow, so they're a lot slower. And we're gonna go ahead and be curious a little bit about performance. So we've seen that we have a lot of waiting time and rotation, and we need to seek, etc. So in order to access something that, well, we'll have the seek time and the rotational delay. This is to get to the block of info that I need, and then I'm gonna go ahead and start the transfer. So I'm gonna transfer. So T is the transfer time, B is the number of bytes that needs to be the bytes that need to be transferred, and then this is the number of bytes on a track. So basically I have a bunch of bytes on a track, and in order to be able to access all the bytes, so I need to rotate each and every time I transfer something my disk in order to cover all the track. So this is why I have a small r here, which is the rotational speed. Fair enough. On average, because remember we need to go this way, or maybe we can go, we need to have a revolution is if we're in here and we need something here, or we need the full revolution if it's something here. So basically on average, the total average access time is TS 1/2 the rotational delay, because again we could be on this side or that side, so it's a 50-50 chance. So on average it's 1/2, and then the transfer time that we need. All right, Now, one of the interesting questions that I asked in class is, a disk at the end of the day is a hardware resource, and a hardware resource that is connected to a computer that is using multi-programming, hence we have coexisting concurrent processes, so they're gonna fight over the disk. And we've seen that whenever we have a resource that processes or threads, doesn't matter, will fight over, we'll need to kind of regulate and control the access to it. So we started comparing the best way to regulate and control the access, and by now we know two approaches. The first one is dealing with the critical resources and making sure that we have some kind of mutual exclusion. So basically it's one process at a time using the proper tools that you already know what tools I'm talking about. It starts with an S. And however, we figure out that maybe it's not that efficient, because imagine that we have multiple processes that are concurrent and they're trying to write and use the disk at the same time. So basically it would be a better idea to have something working in parallelism, if not parallelism, real parallelism, maybe with the impression of parallelism, so making the processes advance and use the disk in this way. And this is where we got inspired from how we use the CPU when multiple processes are trying to use the CPU. So we're going to use, instead of using synchronization, so with semaphores and mutexes, etc., like that, where we can have one process using a resource at a time, well, we can use scheduling, where we can schedule and make sure that we're maximizing the utilization of a particular device. And this is what we did for the CPU, and this is what we're doing for the disk. So basically this is why we talk about disk scheduling. So here again, multiple resources, etc. And what do you want to schedule exactly? So basically the one or the ones, multiple processes that trying to access the particular disk. So now, knowing what you know about the CPU scheduling, you can imagine what kind of policies we could use for disk scheduling. So basically, if I have 6 processes trying to access the disk, well, which one should go first? Well, the easiest ever way is to say that the first one who requested is the one that should go first. It could be based on priority, it could be based the last one, it could be the one that needs the disk the shortest. You can imagine a lot of things. Fair enough? Alright, so let's see. Again, it's me, so I care about performance. So how to improve things? It's either the pessimistics. A pessimistic would say that there's no hope, or my favorite is to say that I'm an engineer, I will find a solution. So let's see, from the OS point of view, not from the driver point of view, if the driver is complex enough, from the OS point of view, well, it's seeing the disk or the disks as one logical entity, right? So at the end of the day, if we use a bunch of independent disks in parallel and present them as one unit, one logical unit to the kernel enhanced to the user, so maybe we can go way faster and have more safety mechanism and redundancy. This is where this RAID standard came in, and RAID stands for redundant array of independent disks, and this is practically in all computers today. So it's a standard. It has different levels, and they're called levels, and there are 7 design architectures that I know of. Maybe there are more now in the new version. And you can see that it's one single logical drive seen by the kernel, right? But I mean, it is physically a set of different disk drives. The whole idea is, depending on the level, the architecture that we're using, one of the 7 options that we have, well, the data could be distributed onto the different drives. And why would that be important, by the way? Why is it important instead of using only one? Let's say we have 2 disks, seen as one logical disk from the OS point of view, and instead of using physically one of the disks only to put everything, we can distribute it. Why would that be important, for instance? Well, you can think that if something wrong happens and the disk that we are storing physically all the data on went bananas, or it broke down. It went rogue, whatever. It's not working anymore. This means that I'm gonna lose all the data. However, if I'm distributing the data across 2 disks, well, this will allow me to recover some of my data, and we're gonna talk about it in a little more detail in the upcoming slide. Right, so this is redundancy, and we can recover as in case of recover data in case of disk failure. So yeah, let's see 3 out of the 7 architectures, so levels that I told you about in the earlier in the previous slide. So RAID 0, disk striping. This is I'm having 2 physical disks seen as one logical disk, right? And here we can see that I have a block here and a block here and a block here. So block 1, 2, 3, 4, 5. So it feels like I'm striping, so I'm distributing my different blocks onto the 2 disks. This is interesting because if I'm losing that one, well, I could have, you know, I still have those blocks. And at the same time, you can notice that I'm filling 1, 2, 3, 4, 5, 6, 7, 8 blocks of data onto my disk. Let's compare it to RAID 1, which is disk mirroring. So here it feels like we're copying the same exact same data over 2 disks. So I'm fitting 4 blocks of data here. So space, space size, efficiency wise, RAID 1 is way smaller, so we're not putting a lot of data in it, only 4 blocks, whether here we're using 8 blocks. So this one is not so good space size efficiency wise compared to that one. So we can fit more blocks using the particular. However, here, if something really goes wrong and I'm losing something, the whole disk, I still have all of the data that I saved. So to make the best of 2 worlds, well, for instance, RAID 5, so another level here that I'm showing you, it's striping, so I'm distributing, and I'm using something that I call parity. So instead of having, an exact copy, well, I'm having different sections from each of my blocks on different disks. And I'm having a disk that will have the necessary information in case of one of the disks is failing. I could still recover the block that I need based on the information that is present on the other disks and the information present on the recovery disk here. Fair enough? So it's the combination of the 2 worlds. Alright, so let's move on to files. So usually files are the things that I find on my hard disk, and we've seen that we have different extensions for my files. So you have a bunch of files, and any dot something means that this file should be you can open it with a particular software tool. And I don't know, is there an MP3 here or something like that? I don't know. So let's imagine that we have an MP3 file. I don't know if you guys tried it or not. Personally, I did back in the days. Of course, that was one of the things that I used to do as a kid, is to try to open an MP3 file using a Word document, for instance, the Word, Microsoft Word, for instance. And then I can see a bunch of characters, meaningless characters, but I mean, it's always fun to see it. And try to modify it to see if it affects the music or the sounds recorded in that particular MP3 file. Alright, so let's try to define in a formal way what files are. So files at the end of the days are sitting on the disks. So if they're sitting on the disk, there's a bunch of data. Data that has some meaningful information from the user point of view, right? Because it's not just random data, it's something that's organized in a way or another, so we can see it. So these are data collections that have some attributes. First off, again, when you turn off your computer or you plug out your disk or USB stick or whatever, the files don't just disappear, right? So they are kind of have some long-term existence. and because they're sitting on the disk and the disk belongs to the they're attached to the computer, and the computer could have multiple programs running at the same time, and multiple programs could use, or processes could use the file, so they are shareable between the different processes. And finally, well, is it something random, chaotic here inside, or is it organized in a way or another? So naturally it's organized in a way or another. Not only that, it's organized inside, get it? So you can see the information presented in a proper way. But also, if you have a bunch of files in a directory, well, they're organized in a way or another. So you can, list them by date, by creation date, by modification, etc., etc. And by the way, those who are familiar with Unix, for instance, everything from a Unix point of view is presented, as files. So even directories, they're just files that contain other files, etc., etc. So files are also data collections that are structured internally. So inside them, data is, organized in a way, and then externally, the files, the bunch of data, they are also organized in a way and presented in a way to the user at the end of the day. So let's explore a little bit this structure that I'm very interested in. Before that, so if we're dealing with files, so there should be some kind of entity that will make things transparent and easy for the users. Fair enough. So the file systems there, they provide a means to store the data. So my long-term existent data, right, they're organized as files, and that's it. Or is it? Now, from a computer science point of view, you've programmed a lot of things in Java. One of the things is how to deal with I/O streams, so how to deal with files. You've kind of tried to do something with files. So go ahead and try to recollect, to remember, to recall the things that you've done inside of your Java programs, for instance. So there were a bunch of functions, right? Using the proper APIs, for instance, to do what? To do something like create a file. If you create, you can delete. If you can create, maybe you can open it in order to write something to it. And if you can open it, you can close it as well. So if you can open to read, to retrieve some information from a file, or you can write to it, so modify it. And this is what you've done as programmers, right, from an engineering point of view. And everything that you've done, you programmed yourself. The non-engineer user of a computer, well, he can create a file by right-clicking on the mouse and saying new file, or they can double-click on a particular file to open it, or click on the X in order to close the file, etc., etc. Fair enough. So let's see the structure now. I'm interested in those three layers here. So you can notice that this is my file, and my file is made out of a bunch of things, and those bunch of things are in turn made of a bunch of other things. Then I don't care about those two for now. Let's focus on the three here. So we can see that we have fields, and then many fields there will constitute a record, and all of the records, they are federated together under a file. So let's do that. So what's a field? So for those, apparently you've had a database course, so basically this is good to know as to refresh your memory. But I mean, you should know what a field is. And someone said it in a very nice way. A field could be seen as a column inside of, some kind of database. So a column that will contain a particular type of information, right? So it's a basic element of data. It contains a single value, and it has, of course, a data type and a length. So imagine that you have a field. We're trying to create something related to an object that is a student. So one of the field could be the ID of the student. Another field could be the name of the student, date of birth, etc., etc. And you can see that they have different data types, of course. An ID is different from a name. Right, so when those fields go together, we're gonna have a record. So if these are the columns, the records could be the lines. So for all the students that we're having, right? So all the related fields could be seen as a unit for a particular object, so by a particular application program. So let's say student A has an ID, has a name, has phone number, date of birth, courses enrolled in, etc., etc., student B, C, etc. And all of these records at the end of the day will constitute my file. And there's, of course, similar nature. Fair enough? So let's see visually an example to make sure that you got it. So here you can see that these are my fields, all right, different columns, and then a bunch of records. And you can see that this is a sheet, an Excel sheet or whatever, any program sheet that we can see. This is the bunch of file. So this is true, and visually it can speak to you, but you can apply it to any file type out there. So the information will be organized, but with different tags here, different fields and different values, etc., etc. And for those who are curious enough about music and sounds, etc., these are the examples here. So you can see the format for WAV files and MP3 files, and at the end of the day is a bunch of fields that you need to fill in with the proper values. And then for each segment of the file, well, it could be seen as a record, and the whole file will be the bunch of records. So here, let me see, and this is a good question if you're to satisfy your curiosity. So let's take a WAV files, and you can see one of the fields that you need to, and this stands on 4 bytes for instance, is the sample rate. And out of curiosity, I asked this question in class. So let's take a WAV file where the sample rate has a very low value. So the number of samples that I've taken in order to create the WAV file is really low. So how good of a quality is my output file, for instance? Well, if the samples are very low, very few, well, the quality will be low. And to have a really good quality, the sample rate should be very big. So I need a lot of samples. So basically there's a price to pay if I do that. What would be the price in that case if the sample rate is very high? So the quality is perfect, but I mean, what would be the price here? Well, it will be the size of the file. The more samples I have, the bigger the size of my file. So it's always a trade-off when it comes to engineering. Alright, so file management systems, and this is of course, again, because we're dealing with the devices and the low layers, so it's a system software, and it has some things to make sure that they happen. So for instance, the file management system is there to guarantee that the data is valid to some extent. Of course, we cannot fully guarantee it. And of course, performance again. It's there to maximize something and minimize something else. So from the user point of view, of course, all we care about is the response time, and you already know what response time is by now. And from the system point of view is the throughput, and of course you know what this throughput is by now. So how many files I can deal with in a defined period of time, and how much time will it take for a user, for instance, if they double click on a file to open it, how much time would it take to open, or how much time would it take to deal with the file, right? This is the sensation, the feeling, how you perceive the reactivity of you dealing with the file. So which one should I maximize and which one should I minimize? Of course, I need to maximize throughput and minimize the response time, right? So because we have different device types when it comes to storage, so we need to have the proper I/O support for each of those heterogeneous devices, right? But at the same time, these are the difference in the low level when I'm going to climb up the layers all the way to the user. From the user point of view, whether you're dealing with the hard drive or you're dealing with the USB stick or something else, a CD, whatever, the floppy disk, right? From a human point of view, it's always double click to open or just move it, etc., etc. So it should be kind of standardized from the human user's eye, right? So a standardized interface for the user, and hence the user processes, because the user is dealing with the proper tools, right? And most importantly, files, it's all about long-term data. So basically I need to eliminate the potential of destroying or losing data, and this is what we talked about. For instance, we could get the benefits of the use of the technologies used in the RAID disks, for instance, as an example. Right. Same here. Go ahead and read it thoroughly again from the user all the way down to the layer, down the layers to the hardware, and then up again, and you can see the different things. So go ahead and read it at home. I'm not going to explain it because I did not explain it in the face-to-face lectures, and it's pretty thorough, so you can understand it on your own. We've been through that over and over and over, so it's just to satisfy your curiosity. And this is more like it. I like this one. Here, I projected it in class, and I asked people to see different sections in that particular schematic, and to try to understand the whole, the big picture from that particular thing. So this is the file system. So let's see. If I start with asking you to place two things, I'm gonna draw a human user, and then let's say the disks or the hardware. So where would you place the human user in that schematic, and where would you place the hardware? Alright, so naturally here we can see that we have user, program, and commands, right? So we have some kind of things to deal with, and then all the way down where we can start to see disk scheduling and stuff like that. So this is where the hardware is, and this is where my human is. So these are the different layers here down to hardware, and here the user. And the thing is, when I'm doing that, well, I'm going through the different layers, right? So here the user dealing with some files, right? It will try to have some kind of operation, so it needs to specify which file I'm dealing with and the thing that I'm trying to do with my file. Have you ever noticed that sometimes you're trying to delete a file and something pops out on your monitor saying that you're not allowed to delete that file? So basically there's some kind of access control, or try to read it or write to it or whatever, it doesn't really matter. So there's some kind of access control when it comes to dealing with files. It will depend if you're a user or a normal user or an admin, etc. And then again, because we're dealing with files, so there's external structure. So this deals with the directory management over there. So my directory management, so external structure, and I have my internal file structure. So I need to know what are the different manipulation functions. For instance, if I'm trying to add records, read from records, etc., etc. And then you can notice here that something went from one side to another side. So here it's the file management concerns, because it's representing all the logical point of view from to make it simple for the user. And then here we're moving towards the actual hardware drive. And then again, if we're dealing with the hardware, this means that I'm gonna go ahead and transform the information, logical information that is at the end of the day a bunch of data, into some blocks. Then I need to go ahead and place main memory to the secondary storage. And if I want to do that, so I'll have to deal with the I/O. So every file will need the block and allocation to the proper device. I might have different storage devices, so I want to put it on my USB stick, for instance, right? And then if I'm dealing with that, this means that I need to schedule, as we said earlier, and then we're going to have our physical blocks in the secondary storage. Where exactly will they be placed in case of a hard disk, for instance? Well, they're going to go on the platters, and more specifically on the tracks and on the sectors. And you can notice here that there's something that we are calling free storage management. What would that be important, by the way? So let's see, imagine that you're trying to put a bunch of films, movies on, hopefully legally, on your USB stick, or a bunch of series, I don't know, Brooklyn Nine-Nine or whatever, hype these days. You're gonna go ahead, from a user point of view, you'd be happy if you could put the whole season on your USB stick. However, for some reason, you managed to fill like 10 episodes instead of 12. Well, for the sole reason is that someone needs to tell you that there's enough space or not on the disk. Fair enough. So I need to go ahead and make sure that I'm having enough free locations on my disk in order to be able to get the files that I want, that the user wants to put on the disk, for instance. Right, so when it comes to file organization and access, so what's file organization? It's all about logical structuring of the records and the way we're gonna, we want to access them. So ideally, I want a real fast access, so short access time, and at the same time, I want it to have an easy update, make sure that I'm not consuming a lot of storage, so the less storage I need, the best for me. And then I want to go ahead and make sure that I can maintain everything in a non-complex way. Can we have some conflicts when it comes to these criteria? Let's think about number 1 and number 3, for instance. Is there any conflict between the two? So short access time means that I can go and get the thing that I need real fast, and at the same time, if I'm using some mechanisms to make sure that I'm compressing in a way or another, so I'm managing the storage in a way or another, well, maybe this will be in conflict with the short access time, because I'm trying to compress the data, hence to extract it will take more time, for instance. Get it? So we could have some conflicts when it comes to criteria. And again, engineering is all about trade-off. Most importantly, of course, I need my file to be reliable, and we talked about that when we talked about disks and in the earlier slides as well. So let's see. I want to access. Let me put myself in the shoes of a compiler. So what is the compiler? A compiler will take the codes, for instance, that you could have written in Java and C. Let me talk about C because I master C more than Java. So in C, and then it's going to go ahead and, so this is a file, a C file. It's going to read the information of it, we've seen in the CA course, for instance, translate it into machine code, go through the different layers in order to get to the ones and zeros that will run on the microarchitecture using the proper ISA, etc., etc. So if I were a compiler, well, I will need in a way or another to read each and every line, each and every record inside of my file from top to bottom, right? So this is sequential reading, so in order, one record after the other. Tick, tick, tick. If I'm a human user now and I want to go ahead, instead of taking all my time, because remember, this is important for a compiler because I need all the information. However, if I'm a human user, I want to go to the record that is number 99. Well, instead of going through everything, it will take me forever. Well, I need to jump straight to record number 99. So how would I do that? Well, all I need to do is use some kind of key or index. Fair enough? So each record has its own key, and I can jump directly to that particular key record. And this is extremely useful for this. How come? Think about it for a second. How can you relate to disks when it comes to the file access method that is direct random? So jump directly with the index. Think about it. This is my disk, made out of tracks, and each track is made out of sectors. If I'm using this method, what would happen to me? This means that I need to go through all of the tracks and all of the sectors in order to get to the particular one that I need. Not good for disks. However, here all I need to do is move the head directly to the corresponding track and to the corresponding sector using the key that is translated in a way or another over there. I mean, hardware wise. We good? And again, this is good. Takes a lot of time, but I mean, it makes sure that I can cover anything. This is good, means that I can go fast and go directly to the thing that I need. What if I I make the best of the two worlds. Well, I can have index sequential, and I can either access things like that or like that. Right, so almost done. A couple of words on OS security. So what is the purpose at the end of the day? And this is the scenario that I used in class. Imagine that one of your colleagues is sitting at the platform using the computer and went to get some coffee. And when they went to get some coffee, some other colleague found the computer and tried to access it. How likely is it possible for that particular second student to be able to access the first student computer? Well, using what we know today, when you're going to turn on the computer, well, the first thing that you need to do in order to be able to use the computer is to enter your username and password. So there's some kind of protection to make sure that the legitimate user can use it and another non-legitimate user cannot use it. Fair enough? So this is the key security of a NOS at the end of the day. Is it should prevent any user slash software, we're going to talk about those in a moment, from gaining unauthorized privileges. And the most basic privilege could be just normal access to the machine. Fair enough? So these are the things. So let me just give you a taste of that. So intruders, also known as hackers, crackers, whatever, I'm going to call them intruders for today in this video, is could be seen in three classes. The first one is someone has nothing to do with the computer, so it's not even a legitimate user, and it can gain access to that computer by hook or by crook, by some method, right? So masquerader, so an individual non-authorized will succeed into penetrating the system to be able to exploit maybe some data or information on a legitimate user account. That's one. So go ahead and imagine a second class. So this one is not authorized. What if, and you've noticed for sure, that sometimes you're a legitimate user. So imagine that you're in a lab at university, for instance. You're working in the lab, and then you're gonna try and use one of the system software. Well, again, something will prompt on your monitor saying that you don't have enough privileges or access or whatever. So basically, you could be a basic user and a non-administrator. So you're a legitimate user, but you're not allowed to use certain parts of the computer, for instance, right? And here is a misfeasor. So a legitimate user is someone that is not allowed to use some parts of the computer, but actually gets to do so. Or sometimes it happens as well, and you should be aware of that. Even administrators also, although they have access to basically anything in a computer, they're not allowed to go ahead and check the information and data of other users without their authorization. So basically, sometimes administrators do misuse their privileges. Misfeasor. And finally, someone that trying to, a normal user or any individual will go ahead and try to access privileges, so they will have, supervisory control over the system to be able to delete some files or evade auditing, or to suppress data that is needed for logging, etc., etc. And this is what we call a clandestine user. Fair enough? So these are the human intruders. Let's talk a little bit about malicious software now. So malicious software, and we covered one of them in the midterm. So what is the short name for malicious software? So if we remove ish here and we remove soft here, so we can call them malware, and this is the known name in the cybersecurity world. So malware is a program that is here to exploit anything that is vulnerable in a computer system. So a vulnerable thing could be any weak point. Fair enough? And here to give you a taste, Think about the early ages of hacking, and imagine that, I don't know, some kind of advanced user on a computer keeps on checking the processes that are currently running. So basically, if you want to introduce some malware, so it's a program, right? It will show on the task manager, process manager list, and then the user can kill it, for instance. So let's think about a way, like especially in the early days, where you can make sure that the user is unable to see it. So some of the colleagues of your colleagues said that maybe we can use a name that is common, or some fake name that of any process that should be there, so the user won't notice that it's a virus, or so, I mean it's a malware or something like that. True, but I want to think about it in a different way. I don't want to create a whole process, a whole program. I want to be even more sneakier. So how can I do that? So all we have to do is sneak a couple of lines of code in any of the programs that already exist, and those lines of code will do the job for us. So first category would be parasites, so fragments of programs, so they cannot exist independently. They need to go into an application program or system program, any kind of process over there, and try to do the harm. So we can see logic bombs such as the fork bomb that we talked about in the midterm, for instance, some backdoors, to open up some ports, some sockets, so we can retrieve information without the user being able to do so. So if we can have fragments of programs, the other category could be a self-contained program, a full program that cannot be seen by the OS as I mean, unless we're using a proper antivirus, etc. But I mean, again, back in the days, and still for things that are unidentified by the antiviruses, so the OS gonna go ahead and in a complete dumb way schedule and run them as if they're normal processes running on the computer. And those could be bots and zombies, so like programs that will do stuff systematically, try to organize attacks on other computers, and go ahead and use your favorite search engine to see the bots and zombie attacks in the US and North America, for instance, and you can see that the number of people being infected without them knowing that they're infected is actually huge. And worms, for instance, are the things that will travel from one email to another email and infect computers, and especially using that. Congratulations, you won something, and you're gonna go ahead and receive the email, open it up, and it will infect your computer. Trojan horse, etc., etc. Yeah. So this is the problem, and we'll need a way to fight back. So the countermeasures would be to just make sure that we are using authentication, so we're not trying to encrypt, etc., to make sure that no one can crack the username and password in order to be able to get in, for instance. Access control, so we can have different categories, and we need to make sure that we're dividing it. So basic countermeasure here. So if we're talking about computers, and this is the case every day, is connected to the internet, a bunch of networks, so maybe we can install some firewalls. And most importantly, and this is what we spend a little bit time in the face-to-face lecture, is to see what is the actual challenge today in today's world when it comes to cybersecurity, so in computer security in general. And from my own experience in my professional life, in one of the companies that I used to work in, the challenge is not per se to fight back. This is relatively easy, and it could be done, and it is done. There's another type of challenge that is actually harder to solve. Can you take a second to think about it? And to help you out, there's an analogy. Imagine that you have a bunch of money in your pockets, and so the money is the data, the things that you have on your computer. And to fight back is just to call the police whenever someone is trying to steal from you. But however, imagine that someone did steal from you and you did not call the police. Why wouldn't you do that? Well, for the simple reason is you're not even aware that someone stole from you. And this is exactly today's challenge when it comes to cybersecurity, is the fact that you can detect that someone in is trying to, you're being under attack, you're getting hacked. And again, from my own experience, some companies, well, they discovered that they were hacked like weeks later, weeks after the attack that happens. And this is what we call intrusion detection systems. And this is where actually the money is today, because the first challenge is we can fight back, but however, we need to make sure that we're detecting that someone is trying to detect the intruders here. Fair enough? So that's it for your OS course this year. Thanks for making it a real nice year, especially those who I'm seeing, and hopefully those who I did not see, I wish you good luck as well, and hopefully I'll be seeing you in the embedded system course next year.